Well, I think we're at the top of the hour, so we're going to get started on our Fast and Furious series here with this morning with Anritsu. And welcome everyone. My name is Steve Case with Electro Rent, and we're going to get rolling. But first, since this is our first in a double series, did want to mention that the second series is in 2 weeks, on June 7th, and we're going to be at that time we'll have Tektronix on and have a little preview of what they're going to be talking about. They actually have a setup here with the Anritsu BERT on top and some tech scopes. So if you, for some reason, didn't get linked into that session, I'm going to put the link in the notes for the show so people can grab that as we go along. But so with that, I think we'll start on our speaker today, which is Hiroshi Goto, or as we know him as G2. Good morning, Hiroshi.
Hi, good morning.
And Hiroshi, G2, could you just increase your volume a little bit so we can hear you a little bit better?
Hello, can you hear me okay?
Yeah, good. And good morning. G2 has a lot of experience with Anritsu in the high-speed area and with the BERT. So his talk today will be quite illuminating as we get into PAM4 subjects. But right before we do that, I do want to mention about Electro Rent, what we do. We have $1.2 billion of inventory and test and measurement equipment all over the world. And we do have a small fleet of Anritsu BERTs and some tech scopes to go along with it. And since these are products that work together now, we're kind of proud to have that capability. And we can actually deliver at all parts of the world. We have warehouses in California, the UK, Beijing, and China, Malaysia, and in India, all over the place. So we can support what's going on. And I think the only other thing I wanted to mention today is that we'll have some questions and answers that we'll be able to do and go to. I will be able to tell you at any point in time about questions if you wanted to take a quick break. And hopefully today, everyone will be here for probably a little bit more than 30 minutes, we're hoping, because we know the content is really good and we don't want to shortchange anyone, so we'll go as long as it takes. And with that, I think Goto, I'm going to make you the presenter now.
Okay, let me start. Thank you very much, everyone, for joining today's webinar. I'm going to present PAM4 BER test and Jitter tolerance test for PCIe6 and beyond. Beyond means like IEEE 400 gigabit Ethernet or 800 gigabit Ethernet. The agenda is I'm talking about market trend shortly and challenge of PAM4 transmissions. Then I'm going to talk about forward error correction. Then lastly, I would like to introduce Anritsu BERT MP1900 receiver test solutions with forward error correction. So first, market trends. The driver is a data center. 5G mobile communication is very widespread. So data centers traffic is growing to support like a cloud computing and video streaming. This is a copy of PCIe roadmap. I didn't know I could share this year 2022 because still confidential. So I just made a copy from last year 2021. And as you can see, almost every 2 years, the price, the data rate or bit rate is doubled. And actually, we just finished the first PCI Gen 5 official workshop last month. And now PCI Gen 6 is will be amended like maybe end of this year or early next year. And you can see now the PCIe Gen 6 64 gigabit per second or transfer speed per lane. Also, this PCIe is a backplane for interconnect and point-to-point connection. The Ethernet IEEE is kind of a leading the standard. And this is a table from 802.3 400G study group. And it shows the mass production of optical module of 100, 200, 400. 2 months ago at OFC show, you can find a lot of optical module of 400G from a lot of new vendors. Then next target is 800 gigabit per second. So that is 200 gigabit per second per lane times 4. And in the near future, 1.6 terabit. So when you say 800 gigabit Ethernet or 100 gigabit Ethernet or 800 gigabit Ethernet, actually it is kind of a consolidated aggregation. So when you say 400 gigabit Ethernet 802.3 CK, that is 100 gigabit per second per lane times 4 lanes. And now to achieve 800, you can use 8 lanes, so that is OSFP or double density QSP-DD type to achieve 800 gigabit Ethernet. And in the near future, 1.6 terabit per second, 200 gigabit per second per lane using 100 Gbaud PAM4 times 8 lane will be 1.6 terabit per second. So what's the challenge of these high-speed transmissions? The key challenge of 400G, 800G, also 64G PAM4 PCIe Gen 6, the major problem is SNR, signal to the noise ratio. Now, compared to the NRZ, you can see 3 eyes. So you automatically lose 10 dB SNR, so signal to the noise ratio, because of the 1/3 of eye height, you will automatically lose 10 dB SNR. And also, electrical interface becomes like a 53G board, so the channel loss or frequency dependent loss, or some people say ISI, gonna be huge problem, the impact to this TRTF degradation. And also crosstalk is a huge problem at this higher frequency. And now the further error correction is kind of a must to make a stable point-to-point connection. The concept of PAM4 is to put 2-bit in one time slot. So NRZ, you have only 0 or 1 data information, but by putting 2-bit in one time slot, you can send 4 different information, 00, 01, 1011, so 4 different combinations, and it represents 0, 1, 2, and 3 levels, V0, V1, V2, V3. So the good thing is you do not increase the actual baud rate to double the bit rate. You can stay the same baud rate. For example, 32G is PCIe Gen 5, 64G is Gen 6, but using PAM4 technique, you do not need to increase the baud rate up to 64, but you can still use 32G baud rate and put 2-bit in one slot. You can double the speed. But again, the disadvantage is degradation of waveform, small I. Now, NRZ, you have a wide I margin here because of the center of the I. So it doesn't matter of this TRTF. However, when you use PAM4 technique, center I, even center I, this TRTF, rising time, falling edge, falling time, eat the margin of the phase. So you automatically lose 9.5 dB SNR by 1/3 of I height, plus because of the ISI, this edge will be degraded. So because of the transmission frequency dependent loss, you will lose the phase margin significantly because of this TRTF. This is the actual I NRZ. The contribution of phase margin is mainly jitter. But for PAM4I, in addition to the jitter, you will lose the I margin because of the ISI channel loss. So historically, NRZ transmissions, the target BR was almost no errors, 10 to the minus 15 or 10 to the minus 12, and chip vendors or module vendors always their target is no errors like a 2 minutes or no errors for 1 hour. But now PAM4, the situation is different. It's going to be very difficult to get error free. So now the target of BER is like a 10 to the minus 5, 10 to the minus 6. The optical 10 to the minus 4, 2.4 times 10 to the minus 4. That is the target. So the BR criteria is like it's easier compared to the NRZ, but mainly because very difficult SNR and signal to the noise ratio. So IEEE specification 18.2 dB or 10 dB loss channel go to your receivers. This is the criteria. But even the pulse pattern generator and error detector, 26G Gbaud PAM4, not difficult to get error free, but 53G Gbaud, 100 kilobit per second transmission, it's going to be very, very difficult when the ISI channel is more than 6 dB. And currently 10 dB, 14 dB, or 18.2 dB, that is the spec of IEEE 400G, 800G. So under this situation, for the error correction is the key technology to make the transmission stable and consistent. For the error correction is done at PCS layers. So the error is corrected in this fake encoding and decoding portion. So once the network is established, this fake encoding and fake decoding correct the errors up to some extent. So now you can find, okay, what is the post fake BR is, because traffic tester or some DUT has function to measure the post BR. However, how do you test prefect and post for the error correction BR for physical layers? For example, SADS, clock data recovery, DFE, these components, you need to test it and make sure no burst error is created by the chip or module. That error should be corrected by FEC. So let me talk about the FEC scheme. This is the example of Reed-Solomon FEC 544, 514. So this is the alignment marker, and this represent the one code word, so one like a packet. And one code word consists of 544 fix symbol. So in this one code word, it consists of 544 fix symbol, and each fix symbol consists of 10 bits. So one code word is almost 10 bit times 500, so 5,000 bit per code word. 544 fix symbol and 10 bit in one fix symbol. And in this case, read Solomon, up to 15 fake error can be corrected. And the difference of ROW, ROW, BR, and fake symbol error is when you have any errors in one fake symbol, any error, 1 or 2 or 3, doesn't matter. It is one fake symbol error. Even 10, all 10 bit is all errors. It is not 10 errors. Raw bit error is 10 bit error, but even all symbols has errors. It is just one symbol errors. And up to 15 fake symbol errors per code word for the error correction can correct that error. So post fake BER will be no errors. Now, this this slide explain how the forward error correction works. So one fake symbol error per code word is correctable. Two fake symbol error correctable up to 15 fake symbol error correctable. And the raw BR 15 fake symbol error will be 15 bit error or 150 bit error, because one fake symbol has 10 bit and can be all errors. So 15 fake symbol error means in the range of 15 bit errors to 150 bit errors. But when the fake symbol error is more than 16, now FEC cannot correct the error. So this code word is trash. It must be abandoned. So now the criteria, used to be 10 to the minus 15, 10 to the minus 12, but now 10 to the minus 5 or 10 to the 6 before FEC. But in addition, this criteria of 10 to the minus 5 raw BR, and it's strongly recommend this error must be corrected by FEC. So no burst errors which cannot be corrected by FEC. That is a kind of a new criteria. So this is just a screen copy of error detectors. So error detector has a function to capture the burst errors when the burst error is uncorrectable, or you can specify how many fake symbol errors per code word just captures errors, and up to 128 different events error detector capture that burst error only. If the burst error is correctable, ED error detector does not capture the burst errors. Only when the burst error is not corrected, so or meet your criteria of number of uncorrectable fake symbol, the ED capture the pattern and up to 128 different events. So by analyzing that capture data, you can tell, okay, now burst error always happen at this specific bit streams, or oh, now the burst error just happen randomly. It doesn't depend on the bit sequence. That kind of analysis is very important when you design the chip and the device. But the chip device doesn't have FEC, so you need some trick to make this kind of burst error analysis. So this is a measurement example of clock data recovery using Anritsu PAM4 BERT. Now you can see raw BER is 10 to the minus 7, so it meets the criteria, and uncorrectable error is -8, which means error count no. So all error of this error is correctable, and you can see this kind of histogram. So this CDR generates some errors, but all errors is correctable. So this is fine, and it meets the criteria of 10 to the minus 6. However, now same DUT, but we change the recipe of SJ and SSC. Now same DUT, error rate is 10 to the minus 7, almost same, 10 to the minus 7. But now it shows some uncorrectable error count 3. So uncorrectable code was 3. So even 10 to the minus 7, the DUT meet the criteria of before FEC. Sometimes the DUT generate uncorrectable error. So now Anritsu error detector has a function. So now when you increase the jitter from 0, no jitter injection, and now injecting the jitter, and you can start seeing some uncorrectable error. So this is a kind of a stressed eye jitter tolerance measurement. And also another test example of, actually this is a 400G transponders test, actual optical networks. So this yellow bar graph is when we add a lot of SJ. This blue line is 400G standard criteria, so worst case scenario. And this DUT pass the criteria because at the worst case scenario, the error rate is 10 to the minus 7 and no uncorrectable error generated. And then, and it increase the SJ, the spec point is 0.1 UI, actually 0.05 UI, sorry, 50 milli UI, 50 milli UI is the criteria. And DUT passed the criteria, then we increase the SJ, and then up to 350 milli UI. Now the DUT starts showing, actually optical transponder showing the error of uncorrectable error. Okay, so lastly, let me introduce the Anritsu BER test solutions. So the Anritsu error detector detects both bit errors and fake symbol errors in real time. Error detector measures every single bit. And you can make a jitter tolerance to use a different criteria. For example, historically, the BER of 10 to the minus 12, or you can specify 10 to the minus X, or you can specify how many errors per XX second. For example, PCIe Gen 5, one error of 32 seconds, or one error for 125 seconds for Gen 5 is okay. But two errors or more that fail. In addition to that criteria, you can add the criteria of uncorrectable error. So you can make a jitter tolerance test using the criteria of uncorrectable error by FEC for the error corrections. And then once you have some uncorrectable error, you can see the distribution of errors, and also you can see the histogram of this uncorrectable error. this data shows details of bit errors. And I just magnify this. So in this case, fake symbol errors, actual raw BR, and uncorrectable BR. And when you click this detail, you can see this histogram, and also total BR, insertion BR, and omission BR. This is a great, nice tool to make troubleshooting. Insertion error is, which means insertion means error detector expect 1, but measured 0. So the bit is inserted to 1. So that is insertion error. The omission error is error detector expected 0, but error detector detect 1. So that is omission error. Oh, the opposite. Omission, yes, that is opposite. Sorry. Okay, so now, as I said, using this criteria, uncorrectable code word, you can make a jitter tolerance test. And from my experience, you can increase a lot of jitter margin if you change to this uncorrectable criteria. If you use like a 10 to the minus 7, you will lose like a 20, 30 milli. But when you use this uncorrectable code word error criteria for the jitter tolerance on your DUT, you can increase the margin, maybe 20%, 30%. And Anritsu BERT has a function to make this jitter tolerance measurement automatically. This is the same slide. So without jitter, error-free, increasing the jitter, and you start seeing the errors. And capture function, you can only capture the error, burst errors, when the error exceed the threshold you set from the GUI. In general, 16 fake symbol errors per code word, but you can specify this number, fake symbols, and uncorrectable fake symbol numbers from the GUI. Okay, last slide, I'm going to show some video of the jitter tolerance. So now DUT has no errors. So now this is the SJ injection, 100 megahertz SJ. I'm increasing the jitter. So now DUT starts showing the errors. Now this point, 250, 260 milli. Now DUT starts showing the errors. And now you can see the details of this MSB and LSB. Also, you can see which transit has errors. So let me go back. So from this table, you can tell which transit will have errors. So for example, 0 to 3, no errors. 0 to 2, no errors. But 0 to 1, you have some errors. Again, same thing here. 2 to 3 has some errors. So this kind of analysis can be done. Okay, let me just explain something. So next month in June, PCIe organization has PCIe Developers Conference on June 21st and 22nd in, I believe, Santa Clara Convention Center in California. And Anritsu and Tech is going to make a live demonstration of PCIe Gen 6 base spec. We will make a stressed eye to meet the criteria of PCIe Gen 6 base spec. And with Synopsys IP, we are going to make a live demonstration of PCIe Gen 6. Also, we have a PCIe Gen 5 receiver LEQ test. So that is a compliance test, exactly same setup as we did in the last workshop. So please visit our PCIe Developers Conference. Okay, Steve, this is it.
Well, that was excellent. I mean, I always knew about the complexities of forward error correction, but PAM4 is very dependent on it, and this was very illuminating. So thank you, G2. That was excellent. At this time, we're ready to take questions if anyone has them. We don't have any questions yet, so I'll just mention that we did put all the handouts in the handout section of the webinar, and you can have those. And we'd love everybody to come to the both of our sessions. So I'm going to put a link in the chat for the next session on June 7th while we wait for any questions to come in, which we don't seem to have any yet. But again, this is state-of-the-art stuff, G2. So that was excellent. Just seeing how you know the number of errors and the video was very good too. It kind of showed in real time how you can affect that. So that was great. No questions are coming up. I do also want to mention that at the end of the webinar, we have a couple of survey questions for you, if you can answer those for us. And with that, I think we're right at a half an hour section. So this is a great timing for us to give everybody back some time.
Probably, yeah. Okay.
So we did send the invite in the chat, but we will be sending some more invites out to make sure that everybody's covered for the second event. And
when you
go
say
ahead.
Sorry. Yeah.
Go ahead.
When you say the convention center is, can you repeat the convention centers next month or what?
Oh, you talk about PCIe Developers Conference?
Yeah.
It's a Santa Clara Convention Center, I believe.
Yeah, I mean the date. I think I got some of the papers.
June 21st and June 22nd. If
Okay.
you can go to Google and type in PCIe Developers Conference 2022, you can find easily the information.
Thank you very much.
Sure.
Thank you, Joe. Anyone else with any other questions? Don't see any, G2, so I think that's going to end it for us. Thank everyone very much for coming, and go ahead and answer our quick survey at the end. And thank you, G2, for
Thank you
great
very much.
presentation.
Thank you very much for joining us. Thank you. Bye-bye.
Bye-bye.